Hello, DockerCon. My name is Kathleen Juell, and I am a developer at DigitalOcean. Primarily, I work on our community web property, doing a mixture of full-stack application development and managing our pipeline and deploy process via concourse to Kubernetes. So today, I'm here to talk to you about how to build and run Node applications with Docker and Compose. But first, just a bit of background on this talk and its topic by way of DigitalOcean's community. Some of you may be familiar with the community platform already. We have a wide range of tutorials, questions, answers, and developer tools designed to spread awareness and knowledge of open source technologies. So the basis for this talk is actually a series that lives on community called From Containers to Kubernetes with Node.js. The motivation for this series was my sense that there's often a divide between guides that discuss containerization and deployment and those that discuss application development. So I was interested in how a full stack series would do, a series that brought those two things together. And just quickly, I want to mention that we now have a wonderful ebook version of the series that you can download for free from community. Finally, one more resource. I have a series called Rails on Containers that also lives on community that aims to do much the same thing as the Node series, basically taking a full stack approach to application development and containerization. Okay, so today I'm here to talk to you about building and running Node apps with Docker and Compose. So first, I'll talk a bit about what goes into building an image. Then I will talk about how to wire up a development setup with Compose. And then finally, some things that you will want to think about when you're setting up for deployment. But first, some hot takes. In all seriousness, before launching into any specifics, it's worth spending a minute getting reacquainted with the problem containers are designed to address. So this slide, for example, shows a Flickr-like application that has a user management piece, a photo management piece, a database adapter, and a front-end piece. So the application gets loaded as a whole onto a virtual machine. Scaling, therefore, involves provisioning more machines. If any part of the application changes, the whole thing needs to be reloaded. So things like application level upgrades become tedious and error prone with lots of works on my machine ambiguity thrown in for fun. In a microservice-based architecture, however, we split the app up into microservices, which are collections of loosely coupled service applications that each perform a single function. Containers are the underlying architecture, underlying foundation for this architecture. So they make it possible to manage groups of identical workloads or deployments and endpoints that expose groups of containers or services. And as you've probably gathered from this image, these are key concepts when you're working with container orchestrators like Kubernetes. Okay, so today we're going to talk a bit about what you can do with containers specifically. So before we get into any code, it's worth taking a minute to talk about containers and virtual machines together. So a virtual machine, good example of a virtual machine would be a DigitalOcean droplet, a remote server. So these servers allow you to run multiple full systems on a single physical host. A hypervisor manages the multiple running machines and shares hardware resources between them. So this is great because it allows for application sandboxing and versioning. It's way more efficient than running several physical hosts, but you still have some bloat, right? Like a full operating system. Containers are like virtual machines, but they provide some additional advantages. They accomplish the goals of sandboxing applications and provide consistent, reproducible runtime environments much more efficiently. Running containers means that you don't need a full operating system, just a container runtime, so Docker. Container image files are generally much smaller than virtual machine files. The spin-up time for containers is generally much quicker. They tend to be more performant than virtual machines. And finally, there are lots and lots of pre-built, pre-configured images available that you can use that are officially maintained, Nginx, Python, Node.js, etc. So now that we've covered some meta-level stuff on containers, let's drill into how you might build an image for a Node application in particular. So first, you want to think about building your base and some of the choices that go with that. You can find a list of images along with explanatory resources for officially maintained images on Docker Hub. In our case, we're going to use an Alpine image for our node base, and using an Alpine image or a Slim image is a great way to minimize the size of your final image. Some things that are worth keeping in mind when using Alpine images are your package availability and compatibility with other systems might be different from what you expect. So Alpine uses the musl library, while many other distros, like Ubuntu, use glibc. So depending on your needs, that could complicate things for you. There have been differences in how these libraries handle DNS resolution, which can really matter in a Kubernetes environment, for example. So for us, for this image, we're going to use the Alpine node base because none of those things affect us. So first, once we set our base with the from instruction, we can add our container level of dependencies. So the application that we're building here doesn't have any additional requirements, but let's say we wanted to add Vim so we could interact with our application files on the container. We could then add a run instruction to add that package. In cases where we needed multiple packages, we can chain these dependencies into a single run instruction. This will help us keep our image layers to a minimum and decrease our overall image size. So chaining the package index update to the add instruction, as we've done here, will also prevent any unintended consequences. Let's say our update image layer is cached, for example, but a new package is added to our application. That could cause us problems, but if we chain things together, it'll let us bust the cache appropriately. Hopefully, no cache, this flag here, prevents the package index from being cached locally, so we don't need to add additional instructions to clean it up following our package installation. Next, we're going to set our working directory and user. Here, we get to take advantage of the fact that our image base has a node user that we can use to avoid running our container as root. In the same way that you would want to avoid running processes on a virtual machine as root, it's a good idea to restrict privileges in a Dockerized environment by running processes as a non-root user where possible. Our next step will be copying our application code over and installing our project level dependencies. When copying your code, again, it's a good idea to think about cache busting. So what we don't want is for our node modules to be rebuilt anytime we make a change to our application code, unless we're actually changing our dependencies. So if we separate out a copy of package.json and package.lock.json from our application code copy, we can actually avoid that situation. So this is a great pattern to follow with other stacks. Like, for example, if this were a Rails app, you would definitely want to do that with your gem file. Here we can also use the chown flag when we're copying our application code to set the appropriate permissions on the code for our node user. And finally, you can see what we're copying the application code from the root of our project over to the working directory that we've specified above. Next, we'll add our expose and command instructions. With expose, we are indicating what port the app will be listening on for connections. And then, as our last instruction, we're going to specify a command to run the application with. In this case, it'll be node app.js, which uses our project's app.js file. If we needed to provide a greater level of specificity here, like for example, if we had some tasks that we needed to perform once our dependencies have been installed and our code copied, we can also add an entry point script or entry point instruction that points to a script that could accomplish those tasks for us. So to build out your scripts, you can always look at the source code for any image to see what the default command is for the image, and then you can write your scripts and commands accordingly. So here, in this case, this image default command is node. Okay. So we can interact with containers in many ways. So some things that we're going to do, we're going to build the image using the docker build command. Anytime you build images, you can always look at them with the docker images command, which can be very useful if, say, you're experimenting with different bases, or you wanted to implement build stages to minimize your final application image size. We're going to run our image with docker run. So we'll be using the D flag, which will run the container in the background. And the P flag will publish the port on the container and map it to the port that we're going to specify on the host, which in our case will be 80. We can always look at our containers with docker ps, and the A flag will give us everything, even things that have stopped. And then docker logs will give us our logs, and we can always exec into a container using docker exec. So here, is an example of the command that we would use if we wanted to exec into our Node application container and get a running shell to it. So it, because we're using that Alpine image, it uses the Bourne shell. So this is the command that we would use to get that shell. All right, so demo time. So I'm going to clear all that. And you can see that in our directory, we have a Docker file already. It does not have a unique name. So what we're going to do when we build is we are not going to use the F flag, which we could use to specify a different Docker file. So we're going to build, we're going to tag this, we're going to call this Docker demo. And we're going to specify the current directory as the build context. So you can see that I've cleared my build cache, so we're getting everything fresh. All right, cool. So now we can run this, docker run. We're calling this docker demo. I'm going to run it in the background. I'm going to publish 8080 to 80 on the host, and we're using docker demo. Okay, so now we can go over to localhost, and we can see our Shark application. Looking good. All right, one final stop. We're going to look at our containers, and we're going to stop this one that we just built. Now we know it's working. And we'll remove that as well. Cool. All right. So we now have our application running, or we've seen how we can do that. But as you probably saw on our application form, we have what looks like input fields. So we're going to need to persist some data. And in order to do this, we're going to have to add a database service to our setup. So we can do this using multiple containers with a tool called Compose, which allows us to define multi-container setups. So we're going to walk through how we could wire up a database service with MongoDB to persist our precious Shark application data. First, though, we want to take care of a few things on the application side to ensure that things run smoothly when we add Compose to our application. Before we add any code, though, it's worth thinking about what Compose is doing and how that might affect our application code. So a service in Compose is an abstraction that allows us to point to a running container. So using Compose and architecting our application as a collection of services will bring it in line with 12-factor principles. So before we set up a Compose file, it's worth thinking about the work that we need to do on the application side with that definition of Compose in mind and with those 12 FAA principles in mind. So the 12 FAA principles that matter to us here are storing the config in the environment and separating it from our code, and then treating backing services as attached resources. So we're not running Mongo locally, right? We're not working on a virtual machine that's running Mongo, and we're not working with an assigned database host, like a separate virtual machine that's running Mongo. So we need to make sure that our database, our code can work with a database host that's dynamically assigned. So for example, if we had a Node application that was already using Mongo, let's say, on the same host, we probably already have database connection information and methods defined in a db.js file. So what we need to do is go in and pull those values out of that file and find a way to pass them in dynamically. So here, for example, is a db.js file that hard codes some connection constants. We can make this dynamic by using Node's process env property, which returns an object that contains the user environment. So instead of hard coding the Mongo connection details, we can read them from the environment. This means we'll need to set them elsewhere. So a local hidden file can be a good way to store secrets apart from your code. Be sure if you take this approach, though, that you log that file into your Git and Docker ignore files. So here is an env file with those variables that we saw earlier in our db.js. If you're working in an orchestrated environment, I highly recommend a credentials manager like Vault, which can provide, obviously, way more security than a local hidden file. Okay, so in db.js, we're going to make sure that we add resiliency here to our code by specifying some parameters around connection attempts. So here we're defining some code that will allow us to set how we try connections and deal with successes and failures. And then finally, in package.json, we want to make sure we have Nodemon, which will allow us to automatically restart our application when we make changes, because certainly, especially in a development setup, we don't want to have to do that manually on the container. Okay, so now we get to write our Compose file. So the first thing that we're going to do is tell Compose what image we're using for our Node.js service. So here, because we're working in development, we're going to build the image locally using that Docker file, which we've located in the context of our current directory. Next, we're going to tell Compose which environment file to use to load that information. In this case, this is just that env file that we just saw. We also want to make sure that we're specifying the Mongo hostname correctly. In our case, it's going to point to our DB database service, which we're going to create next. You'll notice that we've added some volumes here as well. Bind mounts like this one are a key part of developing with Compose, right? Because in this case, this mount will mount the code in our host in our working directory to the container. So we can still work in this local directory node demo, and the work that we're going to do is going to be available immediately and accessible in the container. However, working with bind mounts can lead to some confusion, so it's worth keeping a few points in mind. Whatever is on the host will hide what's on the container in cases where they're not identical, right? So the specific changes that you're making to map to your container, introducing only what's necessary, or if you're spinning up an experimental environment to see how that'll do, could be overwritten by anything that you have locally. So in these cases, a named volume can be a really handy tool. So specifically here, we want only the node modules that we've specified for this version of the project to be present on the container. Or let's say, instead of having a longer running project where we run into dangers, we have just cloned this repo and we haven't installed anything locally, so we want to make sure that we don't have an empty directory that's overriding what's installed on the container. So this named volume will persist the node modules that we install with our Dockerfile instruction and mount those contents to the container, which will hide the bind. So it's helpful to think about doing this with any dependency that you want to version or avoid rebuilding on boot. Okay, and then final word about volumes for Mac users. Thanks to the fact that Macs are not running a Linux kernel natively, file system mounts do not have the same guarantees as they do in a Linux system. So fine-tuning your mount consistency between container and host using things like delegated mounts is one way to deal with this, and it'll make your load times a lot faster. Okay, we can then add our ports option to map port 80 to 8080 on the container, and a command that will override the command that we specified in the image. So in this case, we're running the app with nodemon to ensure those automatic reloads happen after we make changes. And we're also using the wait for tool, which is a wrapper script that uses netcat to pull whether or not a specific host and port are accepting TCP connections. This is to avoid any unintended consequences if, say, our application were to try to connect to our database before our database startup tasks are complete. Compose also has a depends on option to ensure orders of dependency when starting services, but this order is based on whether or not a container is running rather than its readiness. Next, we're going to build this DB database service. For our database image, we can use the official Mongo image rather than building our own locally and then either pushing it up and pulling it back down. And this is because we don't need to do anything specific to the image. Next, in our environment option, we're making use of the default variables that, we're both loading the environment file, right, but then also making use of some of the variables that Mongo is providing for us out of the box. So Mongo initdb root username will create a user with root privileges that are defined in the admin authentication database. And then a Mongo initdb root password will set that user's password. In cases where we wanted a user with restricted permissions, for example, we would want to create a script to accomplish that and then mount that script into the Docker entry point initdbd directory on the container. Finally, we're going to add a named volume to persist our application data so that it's not lost between container restarts. And then finally, at the end of the file, we're going to add a top-level volumes key for these named volumes. Okay, again, many different ways that we can interact with our containers and services. We're going to use Docker Compose upd to build our containers and services and run the containers in the background. We can always list everything with Docker Compose ps. We can get our logs with Docker Compose logs. And again, we can exec into our containers with Docker Compose exec. So, depending on the base that you're using, keep the point in mind that I mentioned earlier about the Alpine shell. And then finally, Docker Compose down will take down our containers and our defined or default network. So in our case, we're using a default bridge network. All right, back we go to demo. Oh, try that again. And we're going to run Docker Compose upd. Awesome. Now, pull this up fresh, localhost again, and what do you know? Got our sharks, and we can add some sharks. So I'm going to go with this megalodon shark, which is an ancient shark. and we're going to submit that, and cool. See it. Create a new shark. Let's do a whale shark. Those are large. Awesome. Okay, so actually, let's test our persistence by taking this down. Okay, so our containers are down, right? But we want to make sure that our application data has persisted. So I'm going to put these back up. I'm not destroying the volume. Cool, okay. So now reload and my volumes have persisted. We can also check that by going to sharks get shark, and there we go. All right, cool. So far we've talked about some things that are specific to development setups of Compose, along with some things that are generally applicable, like name volumes and decoupling credentials from application code. So building on this information, I want to briefly touch on some of the things that you will want to implement when you're getting ready to deploy to production. So when you're working in production, you're going to typically be building and pushing application images to some type of container registry. So instead of building your application locally as part of your Compose workflow, you will likely build and push a versioned image to a repository, which you're then going to pull down to run that app. With volumes, you're definitely not going to want to have any bind mounts between your local application code and your container running in production. So instead, you can use a named volume, which will allow you to mount the code that you've deployed to other containers for reuse. So this is really effective if you need to share your application code between containers. You will likely want to add a web server to your setup. So with a web server, you can do a few things, including adding specificity to how your application handles requests. You can also get certs for your application. And you have a few choices when you are adding your config to your web server container. A bind mount on a config directory or a file will work. You can also build the image locally and push it up, and you can copy your config over as part of that process. So in that case, you can also use the named volume to persist the config. In order to get your certs using, say, a certificate authority like Let's Encrypt, you have a few choices. You can always obtain them for a virtual machine, as you would without containers. However, you can also work with a certbot service using the officially supported certbot image. And this would allow you to go through the entire process of obtaining your certs with containers. So you would get the certs, mount them as volumes, and then mount those to your web server container. And you know how application code, the app code volume here, is being shared between all three of those services, so the app, the web server, and certbot. So if you'd like to learn more about that process, because I'm glossing over it a bit, I have an article on the community called How to Secure a Containerized Node Application with Let's Encrypt, which will walk through the process in way more detail than I have done here. Okay, so that's it for me. Thank you for listening. I'll look forward to engaging with questions, and yeah, enjoy the rest of DockerCon, folks.